95% of the universe is missing, not misplaced, not waiting in some distant corner to be catalogued. Missing, as in we have never seen it, never touched it, never measured it with any instrument we have ever built. Every star you have ever looked at, every planet, every comet, every nebula, every dust cloud drifting through the spaces between galaxies. All of it, every atom of it, every photon that has ever landed on human eyes, accounts for just 4.9% of everything that exists. Sit with that number. 4.9%. If you were trying to understand a painting and someone told you that you could only see 4.9% of the canvas, you would not say you understood the painting.
You would say the painting was mostly hidden from you. That is the situation cosmology finds itself in right now. The universe is mostly hidden from us, not metaphorically, structurally, fundamentally. The physics of what makes up reality has a 95% component that does not interact with light in any way we can presently detect. The figures I am describing come from the Planck satellite mission, whose final results were published in 2018. The Planck spacecraft mapped the cosmic microwave background, the faint glow of radiation left over from the early universe, 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form for the first time.
By analyzing the subtle temperature variations in that ancient light with extraordinary precision, cosmologists were able to reconstruct the composition of the universe. The result is our best current model of reality, called lambda CDM. And it gives us these numbers: 26.8% dark matter, 68.3% dark energy, and 4.9% ordinary baryonic matter. Protons, neutrons, electrons, the stuff that makes up everything you have ever encountered. The remaining 95% divides into two separate mysteries.
Dark matter, by contrast, pulls. It has mass. It exerts gravity. It clumps and clusters and halos around galaxies and galaxy clusters, providing the gravitational scaffolding that holds the large-scale structure of the universe together. They are different problems, different phenomena, and we understand neither of them. But it is dark matter we are concerned with tonight. There is something quietly disturbing about what these numbers imply for the human project of understanding. We have been watching the sky for as long as we have been human. Ancient astronomers mapped constellations, tracked the wandering of planets, measured the movement of the sun and moon with precision that still astonishes. The ancient Greeks argued about the nature of the cosmos. Galileo pointed a telescope at Jupiter.
Newton gave us the mathematics of gravity. Einstein rewrote those mathematics in terms of curved spacetime. For 4 centuries, modern physics has been probing reality with ever finer instruments, and we have built a genuinely extraordinary picture of how the universe works. And all of it, every single discovery, every theorem, every equation, applies to 4.9%. The rest is dark. This is not a failure of science. It is one of science's most honest and humbling achievements. to measure with enough precision to know how much we do not know. The instruments exist. The math is careful. The result stands. The universe is mostly something we have not yet characterized.
We have given it a name, dark matter, and the name tells us nothing except that it does not shine. It is a placeholder, a label for an absence. Consider what it would mean to stand on the surface of a world and look outward and recognize that the vast majority of what shapes the reality around you is permanently invisible to every sense you possess. Your eyes evolved on the African savanna, tuned to detect a narrow slice of electromagnetic radiation, because that band of light happened to be useful for finding food and avoiding predators. You are not wrong to trust your eyes within their domain, but the universe is under no obligation to confine itself to that domain.
The cosmos does not care what frequencies our retinas evolved to detect. It is as it is. And what it is mostly is dark. The question that immediately follows is an obvious one. If dark matter does not emit light, if it does not reflect light, if it does not absorb light in any way we can observe, how do we know it is there at all? The answer is gravity. Dark matter has mass, and mass warps space-time, and that warping affects the things around it that we can see. The invisible leaves its signature on the visible. You cannot see the wind, but you can watch trees bend. Dark matter does not speak to our instruments directly.
It speaks to the ordinary matter around it. And the ordinary matter tells us something enormous and cold and dark is pulling on it from directions we cannot see. The first person to listen carefully to that message was not working with Planck data or computer simulations. He was working with a notebook and a spectrograph at Mount Wilson Observatory in the year 1933, doing the most basic thing an astronomer can do, counting galaxies and measuring how fast they were moving. His name was Fritz Zwicky, and what he found, no one wanted to hear.
Fritz Zwicky was not an easy man to like. His colleagues at the California Institute of Technology described him in terms that ranged from difficult to impossible. He was blunt to the point of cruelty, dismissive of ideas he considered inferior, which covered most ideas, and completely immune to the social conventions that smooth the surface of academic life. He referred to colleagues who disagreed with him as spherical bastards. Spherical, he explained with evident satisfaction, because they were bastards, no matter which direction you looked at them from. He was born in Bulgaria in 1898, raised in Switzerland, and arrived in the United States with a mind that processed astronomy at a frequency slightly different from his contemporaries. He was also, repeatedly, and almost offensively, right.
Zwicky predicted the existence of neutron stars in 1933, the same year he published his dark matter paper, when most physicists considered such objects physically impossible. He proposed that supernovae were the death throes of ordinary stars collapsing into neutron stars, releasing energies that dwarfed anything previously imagined. He cataloged supernovae systematically when no one else thought the project worthwhile. He identified gravitational lensing as a tool for mapping mass distribution years before it became a cornerstone of observational cosmology. In field after field, his intuitions arrived before the consensus was willing to follow. In 1933, Zwicky turned his attention to the Coma cluster. Coma, catalogued as Abel 1656, is a dense and ancient knot of more than 1,000 galaxies gravitationally bound together, sitting approximately 321 million light-years from Earth. It is not a small thing. Stretched across several degrees of sky, the Coma Cluster represents one of the largest gravitationally bound structures in our region of the cosmos, a city of galaxies, each city containing hundreds of billions of stars. Zwicky measured the velocities of the galaxies within the cluster. This is standard procedure. You observe the light coming from each galaxy, measure the Doppler shift, the stretching or compression of wavelengths caused by relative motion, and calculate how fast each galaxy is moving toward or away from you.
From many such measurements, you build a statistical picture of the cluster's internal dynamics, what is called the velocity dispersion, the spread of speeds across the system. What Zwicky found was that the galaxies were moving far too fast. He applied a tool from classical mechanics called the virial theorem. In simple terms, the theorem relates the average kinetic energy of a gravitationally bound system, the energy of motion, to its average gravitational potential energy. If you know how fast things are moving, you can calculate how much mass must be present to keep them bound. Too little mass, and the system flies apart. The virial theorem gives you the minimum mass required for stability. The Coma Cluster was old.
It had been sitting there, a stable gravitational entity, for billions of years. It was not flying apart. Whatever mass was present, it was enough. The virial theorem was satisfied. But when Zwicky compared the mass implied by the velocities to the mass he could actually see, the light emitted by the galaxies, translated through standard astronomical methods into stellar mass, the numbers did not reconcile. Not even close. The visible mass of the Coma Cluster fell short of the dynamically required mass by an extraordinary factor, roughly 400 times short. Let that number settle. Not 10% off. Not a factor of 2. 400.
For every unit of mass you could see in the Coma Cluster, every star, every cloud of luminous gas, there were 399 more units of mass that produced no light at all. If you tried to build a bridge using only the visible supports, knowing the full weight required was 400 times what you had accounted for, you would not call that an engineering uncertainty. You would call it a catastrophic oversight. Zwicky understood the implications immediately. He worked through the numbers carefully, aware that measurements of this kind carried uncertainties. He checked his velocity dispersions. He reconsidered his estimate of the cluster's mass-to-light ratio.
He allowed for the possibility that the galaxies he had measured were not fully representative of the cluster's internal dynamics. And still, after every reasonable correction, the discrepancy remained enormous. He was not looking at a small systematic error. He was looking at a gap so large it could only mean one thing. Most of the mass in the Coma Cluster was simply not there in any form that telescopes could see. There is something philosophically important about the scale of the discrepancy. Had it been a factor of 2, had the visible mass accounted for half the total, the scientific community might have found a way to explain it away. Imperfect measurements, undetected gas, stars too faint to be catalogued.
But a factor of 400 is not an error to be corrected by better instruments. It is a statement about the nature of reality. The universe contains a type of matter that dominates the visible over such an overwhelming margin that no plausible correction to the accounting of ordinary matter can bridge the gap. Zwicky sat with that conclusion and published it. In the polished language of astronomy, in the notation of the virial theorem, in the careful footnotes of a Swiss-educated physicist who had done the math 3 times, and the field looked the other way. The cluster should have been dissolving. The galaxies were moving so fast that the visible matter,
All those stars, all that gas, could not possibly hold them.
Something invisible was providing the gravitational glue. Something with mass but no light. Something present in quantities that dwarfed the visible universe within that cluster by a factor of 400. Zwicky called it Dunkel Materie, dark matter. He published his findings in a paper titled Die Rotverschiebung von extragalaktischen Nebeln, and in it he laid out the case as clearly as his data allowed. There was missing mass. It was not a small discrepancy. It was an overwhelming one. And the only explanation he could find was that most of the matter in the coma cluster was simply invisible. His colleagues were largely unmoved. The response was not hostility exactly. Hostility would have been a kind of engagement.
What the field offered instead was a quiet indifference, the raising of eyebrows, the noting of alternative explanations, the suggestion that perhaps the measurements were imprecise or the models inadequate. Zwicky did not have the cleanest reputation for collegial temperament, which made it easier to set aside his conclusions without feeling the need to disprove them rigorously. His dark matter idea was filed away, not refuted, not confirmed, simply set on a shelf and left there. 40 years passed. Astronomy moved forward. Telescopes improved. Radio astronomy opened an entirely new window on the cosmos. The space race sent instruments above the atmosphere. The universe was mapped in wavelengths from...
But the question of missing mass drifted in the background, neither resolved nor seriously pursued. It took a different question, asked by a different person, to bring it back. Not a question about galaxy clusters, a question about something closer, more fundamental, more quietly devastating in its implications. A question about the way galaxies themselves spin.
A spiral galaxy is a beautiful thing. Seen from above, it spreads like a slow, luminous pinwheel. A dense core blazing with ancient, crowded stars, surrounded by long, curving arms trailing outward through the dark. The Milky Way is one. Andromeda is one. There are hundreds of billions of them scattered across the observable universe, each rotating in the same patient, stately way, arms wrapping outward from the center over spans of time that make human civilization look like a passing breath. The physics of rotation should be straightforward. Our solar system provides a clear example of how gravity works with distance. Mercury, innermost, orbits the Sun in just 88 days, moving at roughly 47 kilometers per second.
Mars, farther out, takes 687 days and moves at only 24 kilometers per second. Neptune, at the cold and distant edge of the solar system, crawls at just over 5 kilometers per second and requires more than 60,000 Earth days to complete a single orbit. The pattern is clear and mathematically precise. Orbital velocity decreases as distance from the central mass increases. This is Kepler. This is Newton. This is how gravity has always worked. Apply the same logic to a spiral galaxy. The core is bright and dense. Most of the visible mass, the stars, the gas clouds, is concentrated near the center. So stars near the galactic core should orbit quickly, and stars far out at the edges of the galaxy's disk, where the visible matter thins and fades, should orbit slowly. The rotation curve, a plot of orbital velocity against distance from the center, should rise steeply near the core and then fall away, mimicking the pattern of the solar system. This was the expectation. Every model assumed it. It seemed to follow directly from everything we knew about gravity. Vera Rubin did not set out to overturn anything. She grew up in Washington, D.C., building a cardboard telescope as a child to watch the stars from her bedroom window.
She went on to earn her doctorate at Georgetown University in 1954, writing a thesis that suggested galaxies might cluster together rather than being distributed uniformly, a suggestion that was initially dismissed and later proved correct. By the 1960s and 70s, she was one of the most careful and precise observational astronomers working in the field, collaborating with instrument builder Kent Ford at the Carnegie Institution. She was interested in the rotation of spiral galaxies. Specifically, she was interested in measuring the velocities of stars and gas across the full disk of a galaxy, from the crowded core all the way out to the faint outer edges.
Ford had built a spectrograph sensitive enough to detect the extremely faint light from stars at the galactic periphery, places where previous instruments had simply lost the signal. For the first time, it was possible to trace the rotation curve all the way to the outer edge of a spiral galaxy. Before she began, she had a prediction in mind. Not her own, the field's. The expectation was universal among astronomers at the time, so deeply embedded in the working assumptions of the discipline that it was rarely stated explicitly. It was simply assumed, the way you assume that a ball thrown upward will come back down. Of course, the outer stars would move more slowly. Of course, the rotation curve would fall. That was what gravity did.
That was what Newton demanded. That was what the solar system demonstrated clearly every day in the measured orbits of 8 known planets. Rubin was not looking to overturn that expectation. She was not, in the language of philosophers of science, attempting to falsify a hypothesis. She was doing observational astronomy, trying to characterize a galaxy with more precision than had previously been possible, using a better instrument, extending the measurement further than anyone had taken it before. The revolution that followed was not sought. It arrived. She started with Andromeda, Messier 31, the nearest large spiral galaxy to the Milky Way, sitting 2.5 million light-years from Earth. Massive, ancient, well-studied.
She measured the Doppler shifts of light across the galaxy's disk with the precision Ford's instrument allowed, calculating orbital velocities at increasing distances from the center. The curve did not fall. It should have dropped off as distance from the center increased, following the Keplerian pattern. Instead, it rose slightly near the core and then leveled out, flat. The stars at the far outer reaches of Andromeda were orbiting at nearly the same velocity as the stars much closer to the center. Not slower. Not the gradual decline the models demanded. Essentially the same speed, held there across the full outer disk of the galaxy. By every calculation derived from the visible mass of Andromeda, those outer stars were moving too fast.
The gravity provided by all the stars and gas you could see was insufficient to keep them in orbit at those velocities. They should have been flung outward billions of years ago. The galaxy should have been shedding its outer arms, dissolving at its periphery, unable to maintain coherence. Andromeda had been spinning like this for billions of years. It was not dissolving. It was stable and intact. Rubin rechecked her measurements. Then she measured other galaxies.
Many of them across the 1970s, each one examined carefully, each rotation curve traced to the outer edges with Ford spectrograph. The same result appeared again and again: flat curves. Velocities that stayed high where they should have dropped. Galaxy after galaxy refusing to behave the way Newton's gravity predicted.
There were two possible interpretations. Either something was wrong with Newton's gravity at these scales. The mathematics that had described planetary motion and falling apples for nearly 3 centuries was somehow incomplete or incorrect. Or there was additional mass in these galaxies that the telescopes were not seeing. Invisible mass, distributed not just in the bright disk, but extending outward in a vast spherical halo, surrounding each galaxy, a shell of matter that could not be detected optically, but whose gravity was holding the outer stars in their orbits. Rubin's preference, and the conclusion that the data most naturally supported, was the second option. The galaxies were not wrong. Gravity was not wrong.
What was wrong was our assumption that the matter we could see was the only matter present. There had to be more, much more, extended far beyond the visible disk, reaching out into the dark, providing the extra gravitational pull that the flat rotation curves demanded. The papers she and Ford published through the 1970s built a case that was difficult to dismiss. Unlike Zwicky, Rubin's evidence was not from a single cluster. It was galaxy after galaxy, each one adding another data point to the same picture. By the early 1980s, the consensus had begun to shift. The flat rotation curves were real. The invisible halos were real.
Dark matter had moved from an awkward footnote in Zwicky's old papers to the working assumption of an entire field. The geometry implied by the flat curves was itself remarkable. For the rotation curve to remain flat, for orbital velocity to hold constant as distance from the center increases, the mass distribution cannot be concentrated at the center, the way the luminous matter is. It must extend outward, and not just outward along the plane of the galaxy's disk. The mathematics requires the additional mass to be distributed in 3 dimensions, in a roughly spherical halo, surrounding the disk on all sides. The halo must extend far beyond the visible edge of the galaxy. It must be wider than the galaxy in every direction.
In mass, it must dwarf what the telescopes can see. For the Milky Way, the numbers work out to something that is difficult to visualize. The visible disk, the flat rotating pancake of stars and gas that gives our galaxy its characteristic shape, extends perhaps 50,000 light-years from the galactic center. The dark matter halo that surrounds it may extend 300,000 light-years or more, nearly 6 times as far in every direction. The halo is not a thin shell at the galaxy's edge. It permeates everything inside it. It fills the disk. It is denser near the center and thinning toward the outer edges, but it is everywhere within that vast sphere.
This was what Rubin's flat rotation curves were telling anyone willing to follow the geometry. Not just that something invisible was present, but that the invisible thing was the dominant structure, and the visible galaxy. The thing we had been calling a galaxy for a century was really a small luminous disk embedded inside something much larger, much more massive, and completely dark. The implication for how we should think about galaxies is one that the mind resists. We draw pictures of spiral galaxies, showing the beautiful arms, the glowing core. Those images are true as far as they go, but they show, at best, the inner fraction of what a galaxy actually is. The true shape of a galaxy is not a flat disk.
The true shape is a vast dark sphere, with a thin disk of stars floating at its center like a coin spinning inside a soap bubble. But the halo Rubin described, this vast invisible sphere surrounding each galaxy, was not just an abstract cosmological structure. It extended inward, through the disk, through the spiral arms, through the space where planets orbit their stars, through the small blue planet in one ordinary solar system, circling a middle-aged yellow star about 26,000 light-years from the galactic center. Through you.
The dark matter halo of the Milky Way does not have a clean edge. It is not a shell sitting at some defined boundary, a wall you would pass through on your way out of the galaxy. It is a diffuse, roughly spherical distribution of particles extending perhaps 300,000 light-years in every direction from the galactic center, wider than the visible galaxy by several times over. And it pervades everything within that volume. It fills the space between the stars. It fills the space between the planets. It is present in the room you are in right now, flowing through the walls, through the floor, through your body, at this moment and every moment. This is not a metaphor or an approximation. The dark matter density of the region of the Milky Way where we live has been calculated from the gravitational effects it produces on the motion of nearby stars. The local dark matter density is estimated at roughly 0.3 to 0.4 gigaelectronvolts per cubic centimeter. What that translates to, in terms of particle flux, is approximately 1 billion dark matter particles passing through every square centimeter of your body every second. 1 billion per second. Through your skin, through your organs, through the dense calcium of your bones, through the nucleus of every atom in your body. A continuous, relentless river of particles that you have never felt, will never feel, and cannot stop. It passed through you when you were born.
It passes through you while you sleep. It will pass through you long after every atom that currently makes up your body has been recycled into the earth. Why do you feel nothing? The answer lies in how dark matter interacts with ordinary matter, or rather, in how it almost entirely does not. Ordinary matter is held together by 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Almost every physical interaction you experience, light hitting your eyes, sound vibrating in your ears, your body pressing against the surface beneath you, is a consequence of electromagnetism. The atoms of your hand and the atoms of the floor you are lying on cannot pass through each other because their electrons repel each other electromagnetically.
The hardness of matter is an electromagnetic phenomenon. Dark matter does not appear to couple to electromagnetism. It does not absorb photons, does not emit them, does not scatter them. It passes through ordinary matter without electromagnetic interaction. It may interact through the weak nuclear force. One category of dark matter candidate, called WIMPs, is defined precisely by this weak interaction. But even if it does, such interactions are vanishingly rare at the scale of individual particles passing through a human body. The most likely scenario is that a single dark matter particle will interact with a single atom in your body, perhaps once per year, perhaps far less often than that. More likely never, across an entire human lifetime.
Consider what it means to be built of atoms, which are themselves mostly empty space. The nucleus of a hydrogen atom is a proton. The proton is roughly 1 femtometer across. The hydrogen atom itself, measured out to the boundary of its electron cloud, is roughly 100,000 times wider than the proton at its center. If you scaled the atom up so that its nucleus was the size of a marble sitting at the center of a large sports stadium, the electron would be somewhere in the stands. Everything in between is void. Dark matter passes through that void as though the atom were not there at all.
We move through the world as though we are solid, because the electromagnetic forces between our atoms and the atoms around us make us functionally impenetrable to ordinary matter. But to dark matter, we are almost entirely transparent. We are not walls. We are ghosts, perceivable by neither side of the interaction. There is a thought experiment worth sitting with. Imagine you could dial down the electromagnetic force, not to zero, just weaker. Weaker enough that the electrons in your atoms no longer repelled the electrons in the atoms of the floor beneath you. You would sink through it. The floor would not feel different to it. You would simply pass through, because the electromagnetic barrier between your atoms and its atoms had been removed.
That is roughly what dark matter experiences all the time. The force that makes the world feel solid to you, that prevents one object from occupying the same space as another, does not act on dark matter. Every barrier is no barrier. Every wall is open space. Every planet is a brief thickening of the void. You cannot imagine what it is like to be dark matter, because you are made of ordinary matter, and your senses have no mechanism for detecting the absence of a force you never knew you relied on. But you are permanently, irrevocably transparent to it. The dark matter does not bounce off you. It does not slow down inside you. It does not scatter.
It does not leave a record of having passed through. It enters on one side and exits on the other, and the only difference between before and after is that a few microseconds of time have elapsed. The dark matter halo did not arrive recently. It was here first. In the earliest epochs of the universe, a few 100 million years after the Big Bang, ordinary matter was a hot, featureless plasma spread fairly evenly through space. Dark matter, which did not feel the same electromagnetic pressure that kept ordinary matter hot and diffuse, began to clump under its own gravity much sooner. It collapsed into filaments and halos, and ordinary matter, cooling and settling, followed the dark matter's gravity inward.
It fell into the wells that dark matter had already dug. Galaxies did not form and then attract dark matter halos. Dark matter halos formed first, and galaxies condensed inside them. We did not produce our halo. Our halo produced us. This inversion is worth sitting with. Every structure you can see, every galaxy, every cluster of galaxies, every long filament of galaxies stretching across hundreds of millions of light years, was seeded by dark matter. The skeleton of the universe is invisible. The visible part, the luminous part, the only part we can directly observe, grew along that invisible framework, the way vines grow along a trellis. The trellis was always there. We see only the vines.
You are the result of a process that began with dark matter. Your atoms were forged in stars that formed in a galaxy that condensed inside a dark matter halo. The halo shaped the conditions that allowed the galaxy to form.
that allowed the solar system to form, that allowed the planet to form, that allowed life to arise, that allowed you to exist and breathe and wonder where you came from. And yet the halo does not know you exist. It flows through you with perfect indifference. It does not distinguish between the space filled by a thinking, breathing human being and the space filled by vacuum. To dark matter, there is no meaningful difference. This is where the discovery stopped and the hunt began.
Knowing that dark matter exists, confirmed by Rubin's rotation curves, by Zwicky's cluster dynamics, by the cosmic microwave background, by the gravitational lensing of distant light, by the large-scale structure of the universe, knowing it exists was not the same as knowing what it was. A particle? What kind? What mass? What interaction, however faint, might allow an instrument buried deep enough underground to catch one? Detectors were designed and built and lowered into the earth. Experiments were cooled to near absolute zero. Physicists waited in silence for a signal. And so the hunt began. Not for something distant, but for something already here.
How do you hunt for something that does not want to be found? Something that passes through walls, through stone, through the planet itself. Something that has been flowing through your body since before you were born, and will continue flowing through your bones long after everything you love has turned to dust. This is the question physicists woke up with every morning for 50 years. Not an abstract question, a practical one. If dark matter is real, if it is everywhere, if it is the majority of everything that exists, then it must occasionally, however rarely, interact with something ordinary. Leave some trace, some whisper of contact that instruments might catch, if those instruments were sensitive enough, and patient enough, and quiet enough.
The leading candidate for that elusive particle, the dominant hypothesis for most of the late 20th century and well into the 21st, was something called the WIMP, Weakly Interacting Massive Particle. The name is almost deliberately humble. Weakly interacting, as in barely, as in almost not at all, but not quite never. A WIMP would be perhaps 100 times the mass of a proton, heavy enough to have gravitational consequences on cosmic scales, heavy enough in sufficient numbers to account for the rotation curves Vera Rubin measured, the missing mass Zwicky calculated, the dark halos that models require to hold galaxies together.
But when a WIMP encounters ordinary matter, when it passes through the nucleus of an atom, the interaction is so faint, so vanishingly rare, that billions of WIMPs could stream through your body every second, and not one of them would leave a mark you could measure. Not one would notice you were there. And yet that word, weakly, contains a seed of hope. Weak does not mean zero. Weak means rare. And if you built a detector large enough, shielded it carefully enough, cooled it precisely enough, and waited long enough, a WIMP might eventually nudge a nucleus just hard enough to leave a signal. A tiny recoil, a flash of light, a measurable event among the silence. So physicists went underground, not metaphorically.
Literally underground. They drilled shafts into mountains. They descended into abandoned gold mines. They built laboratories in the deepest places on Earth they could reach. Because underground, rock absorbs the endless noise of cosmic radiation that would otherwise drown any signal. Every second, the surface of the Earth is struck by a rain of particles from space. Muons, protons, secondary radiation cascading from interactions in the upper atmosphere. At the surface, this rain is constant and overwhelming. A detector looking for rare interactions cannot function in that noise. But beneath a mile of solid rock, the rain reduces to a trickle. The interference drops by orders of magnitude. The instruments can finally hear the difference between something and nothing.
In the Black Hills of South Dakota, 4,850 feet beneath the surface, in a cavern carved out of rock that was once mined for gold, scientists built Lux Zeppelin. The name is an acronym assembled from its predecessor experiments. The machine itself is 7 tons of liquid xenon, cooled to a temperature of -100 degrees Celsius, suspended inside a titanium vessel, inside a tank of purified water, inside a cavern that required months of excavation to prepare. Xenon is used because it is extraordinarily pure and extraordinarily dense. A xenon nucleus is large, providing a target for the dark matter particle to strike.
And crucially, xenon can be made almost perfectly free of radioactive contamination. Every trace of uranium, thorium, radon, anything that might mimic a signal is removed with painstaking care. The xenon inside Lux Zeppelin is some of the purest substance ever assembled by human hands. When a WIMP strikes a xenon nucleus, the nucleus recoils, just slightly, just enough to release a flash of ultraviolet light inside the liquid, and to ionize some of the surrounding atoms, freeing electrons that drift upward through the liquid under an electric field until they reach a gas pocket above, where they create a second flash. 2 signals, the first from the collision itself, the second from the drifting electrons, each lasting microseconds.
Together they form a distinctive double pulse pattern, a fingerprint that distinguishes a genuine nuclear recoil from anything else the detector might mistake for one. The software watching for this pattern runs continuously. The data is checked and rechecked. Researchers compare the shape of the signals, their timing, their location within the xenon volume. Events near the walls of the detector, where contamination is more likely, are flagged and excluded. Only events near the center, far from any surface, in a volume of the purest possible xenon, are considered candidates. 8,000 miles away, in Sichuan province in China, under 2,400 meters of rock in the Jingping Mountains, the deepest underground laboratory in the world, scientists built Panda X4T, 4 tons of liquid xenon.
The same principle, the same silence, the same waiting. The Jinping Mountain provides more rock above the detector than almost any other site on Earth, reducing the cosmic ray background to near total erasure. In central Italy, beneath the Gran Sasso Massif along the highway that tunnels through the Apennines, the Ginanti experiment extends the same logic again. More xenon, better shielding, more refined electronics. 3 experiments, on 3 continents, all listening for the same sound in the same silence. What they heard was nothing. Not almost nothing. Not a hint. Not a marginal excess of events that might, with more data, resolve into a signal. Nothing. After decades of refinement, after Lux, after Xenon 1T, after Pandex I and Pandex 2 and Pandax 4T, after Lux Zeppelin began its run. The silence from these detectors has been total. The sensitivity of these experiments is now so extraordinary that they have ruled out the interaction strength that the original WIMP models predicted. They have gone past that point. They have gone significantly past it. If a WIMP existed and interacted with ordinary matter as strongly as the original theory suggested, these experiments would have found it by now. This is not speculation. The math is straightforward. The failure to detect anything is a result. This is one of the strangest outcomes in the history of modern physics. Experiments designed to fail only if dark matter does not exist, and they have not failed, they have worked. The xenon is there, the instruments function, the backgrounds are understood, and still, nothing. But absence is not the same as impossibility. Every null result narrows the space of what dark matter could be. Every year of silence tells physicists that if WIMPs exist, they interact with ordinary matter even more weakly than the models assumed. The detectors are not failing. They are succeeding at eliminating possibilities. Each empty result is a sentence that begins, "Whatever it is not this. Whatever it is, it does not interact this strongly. Whatever it is stranger than the most natural version of our theories." There is something deeply disorienting about that kind of knowledge. You can spend a lifetime learning what is not true. You can eliminate candidate after candidate. You can build instruments of extraordinary precision and use them to confirm again and again that the thing you are looking for is not quite here, not quite in this form, not quite this kind of particle. And the thing itself continues to pass through you, unnoticed and unperturbed, completely indifferent to the decades of human efforts spent in its pursuit. Some physicists have begun to suggest that the era of WIMP-focused searches may be reaching its natural limits, not because the searches have failed, but because they have succeeded so completely at ruling out the parameter space where WIMPs were expected to live.
The territory of allowed possibilities grows smaller each year. What remains is not the absence of dark matter. It is the growing certainty that whatever dark matter is, it is not the particle we most expected it to be. The underground laboratories continue to run. The xenon stays cold. The data accumulates. But the conversation has shifted. Physicists are asking whether the most comfortable assumption that dark matter is a single heavy particle interacting through the weak nuclear force was always too convenient. Too much a product of what our existing theories made easy to calculate, rather than what the universe actually chose to build. The universe, it turns out, is not obligated to be convenient.
Long before the WIMP experiments went underground, a different kind of physicist was working on a completely different problem. It had nothing to do with dark matter. At first, it was about symmetry, about an irritating inconsistency in the equations governing the strong nuclear force, the force that holds atomic nuclei together. The mathematics of quantum chromodynamics, the theory of quarks and gluons, predicted that the strong force should distinguish between matter and antimatter in its behavior, should behave differently depending on whether time runs forward or backward, should violate a symmetry called CP symmetry. But, experimentally, it does not. The strong force respects CP symmetry with extraordinary precision, far more precisely than the theory has any obvious reason to demand. Physicists call this the strong CP problem. It is not a catastrophic failure of the theory. It is an unsettling fine-tuning. The mathematics permits a violation.
The universe does not appear to exhibit one, and no one knows why. In 1977, Roberto Pache and Helen Quinn proposed a solution. They suggested that this symmetry was not an accidental fact about the universe. It was dynamically maintained by a new quantum field that permeated all of space, a field that adjusted itself continuously, rolling to the minimum of its potential energy, and in doing so, driving the CP violating parameter to zero. It was an elegant idea. And like all quantum fields, this one would have a corresponding particle, an excitation of the field that could be produced and detected in principle.
Frank Wilczek and Steven Weinberg independently worked out the particle's properties. Wilczek gave it its name, the axion. After a brand of laundry detergent, reportedly, because the particle cleaned up a messy problem, nobody thought it had anything to do with dark matter. Then people started doing the calculations. An axion produced in the early universe would be extraordinarily light. Not 100 times the mass of a proton like the WIMP, but perhaps 1 trillion times lighter than a proton. Far lighter. Lighter than a neutrino. Lighter than almost anything in the Standard Model. But because of this lightness, axions would be produced abundantly in the early universe. They would be stable. They would not decay.
They would accumulate over cosmic time, filling the universe like an invisible, featureless fog. And because they are so light, they would move slowly, clustering under gravity, much as cold dark matter is expected to behave. The numbers worked out. An axion in the right mass range could account for the observed dark matter density of the universe, could explain the rotation curves, could provide the gravitational scaffolding for the cosmic web, while also solving the completely unrelated problem of why the strong force respects CP symmetry. This is the kind of coincidence that physicists take very seriously.
When a particle invented to solve problem A turns out to also be the solution to problem B, and the two problems have nothing obviously in common, it suggests that the particle might actually exist. But detection is another matter entirely. An axion interacts with ordinary matter even more feebly than a WIMP. It carries no electric charge. It does not participate in the strong nuclear force. Its only coupling to the particles of the Standard Model is through a faint interaction with photons, electromagnetic radiation, that becomes significant only in the presence of a very strong magnetic field. In a strong magnetic field, an axion has a small probability of converting into a photon. A real photon, one with a specific frequency determined by the axion's mass.
This is the principle behind the axion dark matter experiment, ADMX, located at the University of Washington in Seattle. The experiment consists of a powerful cylindrical magnet, a superconducting magnet chilled to 4 Kelvin, generating a field several times stronger than a hospital MRI machine, surrounding a hollow metal cavity. If axions are drifting through the laboratory at this moment, as they should be if they constitute dark matter, some tiny fraction of them will convert into photons as they pass through the magnetic field. Those photons will have a specific microwave frequency. If the resonant frequency of the metal cavity is tuned to match that frequency, the cavity will amplify the signal, and a sufficiently sensitive detector might pick it up. The problem is that no one knows the axion's mass precisely enough to know which frequency to tune to. Theoretical estimates span many orders of magnitude, so ADMX works like a radio receiver slowly turning its dial, scanning frequency by frequency across the possible range, pausing at each frequency long enough to confirm the absence or presence of a signal, then moving on. The sensitivity required is extraordinary. The signal would be far weaker than any radio transmission, far weaker than the thermal noise of the apparatus itself. To hear it, the entire experiment must be cooled to millikelvin temperatures, within fractions of a degree of absolute zero, so that the thermal vibration of the atoms in the detector does not overwhelm the signal.
The amplifiers used to boost the output are quantum amplifiers, developed originally for quantum computing research, operating at the boundary of what quantum mechanics permits for sensing individual photons. Researchers entering the laboratory wear special suits. Their body heat is a source of thermal interference that must be controlled. The instruments are shielded from every external electromagnetic source. The entire apparatus exists in a state of deliberate, extreme, painstaking quiet. What they are listening for is a murmur from the beginning of time. If the axion is real, it formed in the first microseconds of the universe's existence, when the temperature was so high that quantum fields were in violent excitation.
It has been drifting through the universe ever since, through the formation of the first stars, through the birth and death of generations of galaxies, through the long cooling of cosmic time, through the formation of the solar system, through the entire history of life on Earth. It is passing through the walls of the laboratory in Seattle right now, possibly converting into a photon in the magnetic field, possibly producing a signal that the cavity would amplify, if only the cavity were tuned to exactly the right frequency. There is something philosophically vertiginous about this image. A signal 14 billion years old, carrying information about the earliest moments of time, arriving in a refrigerated basement in the Pacific Northwest.
And the only barrier between us and that signal is not distance and not time, but tuning. We may be one frequency adjustment away from hearing it. We may have already scanned past it without knowing. So far, ADMX and related experiments, including Haystack at Yale and CAP in South Korea, have scanned portions of the mass range where theorists believe the axion most likely hides. They have found nothing. But the silence here is different from the WIMP silence. It is not the silence of a single experiment listening on all frequencies at once. It is the silence of a patient scan, frequency by frequency, through a range that could take decades to cover completely. Each frequency scanned without a signal is ruled out.
Each ruled-out frequency slightly reshapes the map of possibility. The search space narrows, not quickly, but measurably. There is a kind of strange optimism built into this method. You cannot prove the axion does not exist, but you can keep closing the exits, one by one, until either you find the signal or you run out of room for it to hide. And the theoretical case for the axion has, if anything, grown stronger over time. The strong CP problem has not been solved by any other mechanism. Lattice QCD calculations have refined the expected axion mass range. String theory models and grand unified theories predict particles with axion-like properties. The axion has remained stubbornly plausible, even as the WIMP has faltered.
We are reading the universe like an ancient text in an alphabet we do not know. We suspect the words are there. We can see the marks on the page. We have built extraordinary instruments to decode them. We are working our way through the text, line by line, character by character. And the detectors listen. In refrigerators, and in tunnels, and underground, and in converted laboratories, listening for something that may or may not be there. At a frequency we may or may not have guessed correctly. Listening with the patience that science demands when the universe does not volunteer its answers. The patience required is not merely scientific.
It is something closer to what it means to take a question seriously, to commit to it for decades, across generations of researchers, without the guarantee of a result. To say, this might be real, and if it is, we will find it, even if it takes longer than a career, even if it takes longer than a lifetime.
Everything described so far is, in its essence, absence, missing mass, missing signals, flat rotation curves where a decline should have been, detectors that heard nothing after years of waiting, experiments that ruled out possibility after possibility and returned empty-handed. The evidence for dark matter is overwhelming in its aggregate, but most of it is evidence of shape without substance. The impression of something heavy in places where nothing visible could account for the weight. But there is one observation that cuts through all of that. One event in the visible universe where dark matter did not merely leave a statistical shadow or a gravitational anomaly, where it stepped, just briefly, into a configuration that let us see its outline against the light. It happened 4 billion light-years away.
2 galaxy clusters, each containing hundreds of galaxies, trillions of stars, and vast clouds of superheated plasma gas, collided with each other at a speed of approximately 3,000 kilometers per second. 3,000 kilometers per second, 1% of the speed of light. Fast enough to cross the width of the continental United States in less than 2 seconds. This is the speed at which 2 of the most massive objects in the visible universe met. The result of that collision is now catalogued as 1E065756. Astronomers call it the bullet cluster because of the characteristic shape of the smaller cluster that punched through the larger one.
It sits in the constellation Carina, 4 billion light-years distant, and it has become the most important piece of direct evidence for dark matter that astronomy has yet produced. Understanding why requires understanding what happens when galaxy clusters collide. The scale of such a collision is almost impossible to convey. Each of the 2 clusters in 1E065756 contains hundreds of individual galaxies, and each galaxy contains hundreds of billions of stars. The total mass of each cluster reaches into the quadrillions of solar masses, and yet the collision happened.
Not because the clusters aimed for each other, but because gravity is patient and space is curved, and over billions of years, 2 massive concentrations of matter fell toward each other along a path set by the geometry of the early universe. The collision did not happen quickly by human standards. At 3,000 kilometers per second, the 2 clusters required hundreds of millions of years to fully interpenetrate. Stars were born and died inside the individual galaxies, while the clusters were still approaching each other. The shock waves that the gas clouds drove through each other propagated at speeds that, vast as they were still slow by the standards of the event's duration. The bullet cluster is not a frozen instant.
It is a snapshot of a process that has been unfolding for geological timescales. When 2 clusters meet, the individual galaxies within them, vast as each galaxy is, mostly pass through each other without collision. Galaxies are almost entirely empty space. The distances between stars within any galaxy are so vast that even when 2 galaxies merge, direct stellar collisions are vanishingly rare. The galaxies interpenetrate like 2 clouds of smoke, drifting through each other,
But the gas is different. The hot plasma that fills the space between galaxies in a cluster, diffuse, superheated to tens of millions of degrees, glowing in X-rays. This gas is the dominant form of ordinary matter in any cluster. It outweighs all the stars in all the galaxies combined.
And unlike stars, this gas is a fluid. Fluids interact when they collide. They press against each other. They generate shock waves. They heat each other further. They are dramatically decelerated. NASA's Chandra X-ray Observatory was directed at the bullet cluster, and what it revealed in X-ray wavelengths was exactly what this model predicts. The hot gas from both clusters had been catastrophically decelerated. The two gas clouds had slammed into each other and were still interacting. Piled up near the center of the collision, compressed into a compact, brilliant region, heated by the shock to temperatures even higher than before. In X-ray images, this region is obvious. It is the brightest, most concentrated mass of visible matter in the system. Then astronomers did something different.
They used gravitational lensing. Gravitational lensing is the technique of using massive objects as natural telescopes. Mass bends light. Any mass, not just visible matter. A massive foreground object will distort the images of background galaxies, stretching and warping them in patterns that reveal the distribution of mass in the foreground, regardless of whether that mass emits any light. By carefully measuring the distortions in thousands of background galaxies behind the bullet cluster, astronomers were able to reconstruct a map of where the total gravitational mass was concentrated. This map had nothing to do with the X-ray map. The gravitational mass, the bulk of the matter in the system, was not centered on the bright gas. The two mass concentrations had continued moving forward.
They had passed through each other and kept going, leaving the hot gas stranded at the center like debris after a collision. The mass was out ahead of the gas, far ahead, separated by millions of light years. This is the critical point. This is what makes the bullet cluster different from every other piece of dark matter evidence. If the apparent extra gravity were not due to a separate component of invisible matter, if it were instead a modification of the law of gravity, the way theories like Mond propose, then the gravity should follow the ordinary matter. The lensing map should point to where the gas is, since the gas is where most of the ordinary matter lives.
There would be no reason for the gravity to be out ahead of the gas, in the empty space where the galaxies traveled. But the gravity was out ahead of the gas. Precisely where you would expect it to be if the clusters were surrounded by massive halos of dark matter. Dark matter that, unlike the gas, did not interact electromagnetically when the clusters collided, did not slow down, did not pile up, simply continued on its original trajectory as if nothing had happened. The dark matter halos passed through each other like two ghosts walking through the same wall. Think about what this means physically. Two halos, each containing the gravitational equivalent of quadrillions of suns, moving at 1% of the speed of light, meeting head-on,
and passing through each other without decelerating, without scattering, without exchanging momentum in any way that left a visible trace. The gas, which interacts electromagnetically and therefore behaves like a fluid in a collision, was stopped, dramatically stopped, compressed into a bright bow shock at the collision interface, heated to tens of millions of degrees. But the dark matter continued on its original trajectory as if the other cluster were not there at all. This behavior has a name in physics: collisionless. Dark matter, if it exists as a particle, appears to be essentially collisionless,
meaning that dark matter particles streaming through a region of space filled with other dark matter particles experience no interaction beyond the slow pull of gravity.
They do not scatter off each other the way gas molecules scatter. They do not thermalize. They do not exchange energy through close encounters. Two streams of dark matter can pass through each other the way two beams of light pass through each other, each continuing on its original path, unaffected by the presence of the other. The gas, ordinary, electromagnetically interacting matter, got caught. The dark matter did not, and the gravitational lensing map, reading the invisible from its effects on light, showed exactly where each dark matter halo ended up. When the paper was published in 2006, it was received as close to definitive evidence as the field had seen, not definitive evidence of what dark matter is.
Not a detection of the particle, but definitive evidence that dark matter is a real physical component of the universe. Separate from ordinary matter, concentrated in halos around galaxy clusters, and capable of behaving differently from ordinary matter in a collision because it does not interact electromagnetically. Alternative gravity theories struggled to accommodate this. Some modified gravity proposals could explain the rotation curves of individual galaxies without dark matter. Some could explain the large-scale structure of the universe. But explaining the bullet cluster, explaining why the gravity is physically separated from the ordinary matter by millions of light-years, requires dark matter, or something that behaves indistinguishably from it. There is something to be said about the technique that made this observation possible.
Gravitational lensing. Using the curvature of space-time caused by mass to distort the images of background objects, was predicted by Einstein's general theory of relativity in 1915 and first confirmed during the solar eclipse of 1919. It was a triumph of theory over intuition. Mass, Einstein said, does not merely attract other masses through some mysterious action at a distance. Mass curves the very fabric of space-time. And anything that moves through that space-time, including light, follows the curves. A massive foreground object bends the path of light from a background object, just as a lens of glass bends the path of light passing through it. But Einstein's lens does not care what the foreground mass is made of.
Ordinary matter, dark matter, it does not matter. What matters is the mass and the curvature of space-time it produces. This is what makes gravitational lensing such a powerful tool for dark matter research. You do not need the mass to interact with your instrument. You do not need it to emit light or absorb it. You need only to measure the distorted images of objects behind it, and from those distortions, reconstruct where the mass is and how much of it there is. In the bullet cluster, this technique read the mass distribution of a 4 billion light-year distant collision with enough precision to locate the dark matter to within a fraction of the system's total extent. There is a particular quality to the bullet cluster evidence. It does not comfort. It does not answer the deep questions. It tells you only that dark matter is real, that it is massive, that it is something genuinely distinct from ordinary matter, that it travels through other matter without interacting, and then it stops. It draws a shape without naming the thing inside the shape. It confirms the existence of the unknown without revealing what the unknown is. 4 billion light-years away. a collision that began and ended billions of years before the Earth existed. The evidence of it traveled to us at the speed of light across cosmic time. Encoded in the bent images of galaxies we can barely resolve.
And what it tells us is that the majority of the mass in those two clusters is something that passed through a catastrophic collision without leaving a scratch. Whatever that something is, it passed through an impact that would have vaporized any ordinary matter it encountered. It emerged unchanged on the other side. It is still moving, still drifting outward from the point of collision, still invisible, except in the warping of light from galaxies far beyond it. The universe left us evidence. It just did not leave us an explanation.
Step back now, far back, not from a single galaxy cluster, not from a collision 4 billion light years away. Step back from all of it, from individual stars and galaxies, from the experiments in underground laboratories, from the equations and the null results, and try to see the universe at its largest scale. Step back until galaxies are specks, until galaxy clusters are barely visible points of light, until the observable universe, all 13 billion light-years of it in every direction, fits inside something you might imagine holding, impossibly, in a pair of hands. At this scale, the universe is not uniform. It is not smooth. It is not a featureless fog of matter extending equally in all directions. It is a web.
Long filaments of matter stretch across vast distances, connecting dense nodes of galaxies like threads between cities. The nodes are clusters, enormous concentrations of thousands of galaxies, bound together by their mutual gravity. Between the filaments are voids, regions that are nearly empty of both galaxies and matter, some stretching hundreds of millions of light years across. The distribution is not random. It is structured. It is organized. And that organization was not created by the galaxies within it. It was created by dark matter. In 2005, Volker Springel and his collaborators published the Millennium Simulation. It was, at that time, the largest and most detailed computational model of.
Using the most powerful supercomputers available, the simulation tracked the gravitational evolution of 10 billion simulated dark matter particles across a volume representing a cube of the universe, 230 million light-years on each side. The simulation did not start with galaxies. It started with dark matter alone, distributed almost uniformly, with only the faint fractional density variations imprinted on the universe by quantum fluctuations during inflation. Variations we can still observe today in the cosmic microwave background. These variations are tiny. The denser regions are only 100,000th more dense than the sparser ones. But gravity is patient. And over 13 billion simulated years, gravity amplified those tiny differences into structures of extraordinary scale.
They are not classical. They are quantum. In the first fraction of a second after the Big Bang, during a period of accelerating expansion called inflation, the universe underwent a violent expansion that stretched quantum-scale variations in the density of space-time to macroscopic scales. The smallest possible fluctuations
those governed by the Heisenberg uncertainty principle, were blown up to the size of galaxy clusters, of superclusters, of the largest voids. The structure of the universe today, the filaments and nodes and voids of the cosmic web, has its origin in quantum mechanics, in the irreducible uncertainty that prevents any region of space from being perfectly, exactly uniform. This is one of the most vertiginous facts in modern cosmology. The particular galaxy cluster you live near, the particular filament your galaxy sits on, the particular void your local supercluster borders. These things exist because of random quantum fluctuations in the first instance of time, fluctuations that had no deterministic cause, that arose from the fundamental indeterminacy of quantum mechanics, and that were then frozen into the geometry of space by inflation and amplified by gravity over 13 billion years. A different draw from the quantum lottery would have placed your galaxy elsewhere on the web, would have placed your sun in a different galaxy, might have placed no sun at all in your neighborhood of the cosmos. The web we inhabit is this particular web. The dark matter organized itself according to this particular set of initial fluctuations, and ordinary matter followed, and stars formed, and one of them, 4.5 billion years ago, formed a planet at a distance favorable to liquid water. The chain of contingency that leads from quantum noise in the first microseconds of the universe to a thinking creature wondering about its origins is unbroken. Dark matter is one of the links. In the denser regions, dark matter fell inward on itself. It clumped. The clumps grew by pulling in surrounding matter. They merged with neighboring clumps. The merged structures grew larger, pulling in more.
Over billions of years, this process produced halos, roughly spherical concentrations of dark matter, ranging in mass from smaller structures like the halo surrounding the Milky Way up to the enormous halos of galaxy clusters. But the halos were not isolated. They were connected. Between the halos, gravity continued to act. Dark matter that had not yet fallen into any halo was slowly pulled toward the nearest concentrations, flowing along invisible channels determined by the initial density pattern. These channels became filaments, long, thin strands of dark matter connecting halo to halo, node to node. The filaments are not dense at their centers. They are diffuse rivers of slowly flowing dark matter.
But they carry mass, and their gravity is enough to direct the flow of ordinary matter that follows them. The result when the simulation reached the present epoch of the universe was unmistakable. A cosmic web, a three-dimensional network of filaments and nodes and voids stretching across the entire simulated volume. The visual resemblance to a biological structure, to a neural network, to a mycelial mat, to the branching patterns that recur across scales in nature, is striking and has been noted by many observers. But it is not metaphor. It is structure. It is the largest structure in the universe, and it is made of matter we cannot see.
When the Sloan Digital Sky Survey completed its mapping of the real universe, cataloging the positions of hundreds of millions of galaxies across billions of light years, measuring their distances using the redshift of their light to construct a three-dimensional map of the observable cosmos, what the astronomers found matched the simulation with extraordinary precision. Not approximately, not in a rough qualitative sense. The statistics of the real cosmic web, the distribution of void sizes, the thickness and clustering of filaments, the masses and separations of galaxy clusters, matched the dark matter simulations quantitatively. The real universe is organized the way the simulations said it would be, if dark matter is real and cold and behaves the way the models assume. This agreement is not incidental.
It is the foundation of modern cosmology. The conclusion it demands is this: dark matter collapsed first. In the early universe, before the first stars ignited, dark matter began to cluster under its own gravity. It formed the first halos. It laid down the filaments. It established the web. Then ordinary matter, gas and dust and hydrogen and helium, the raw material of stars, fell into the gravitational wells the dark matter had already dug. It flowed along the dark matter filaments. It pooled at the dark matter nodes. And there, at the intersections of invisible threads, stars began to form. Galaxies did not create the cosmic web. The cosmic web created galaxies.
Everything you can see with any telescope, every galaxy ever imaged, every star catalogued, every planet inferred, all of it accumulated at the intersections of a structure whose mass is invisible. The luminous universe is not the primary structure. It is the residue. The decoration hanging from a skeleton made of something we cannot detect, cannot identify, cannot touch. Our own galaxy, the Milky Way, is embedded in the Laniakea supercluster, a gravitationally defined structure 500 million light-years across, containing the mass of 100 quadrillion suns, home to over 100,000 galaxies. Astronomers named it in 2014 when analysis of galaxy velocities allowed them to define its boundaries. The name means immeasurable heaven in Hawaiian. Our galaxy is not at its center.
We are somewhere on the outskirts, on a filament that curves toward the great attractor at Laniakea's gravitational core, a region of concentrated mass, pulling every galaxy in the supercluster toward it. We are on a thread, moving along it, unable to feel the motion, but participating in it across timescales too long for the span of human civilization to register. That thread is not made of stars. It is not made of gas. It is dark matter filament, shaped by the gravitational dynamics of the early universe, billions of years old, stretching across distances that make the Milky Way, with its 200 billion stars, look like a single grain of sand on an endless beach.
Consider carefully what this means for any honest account of where we come from. The atoms in your body were forged in stellar cores. Those stellar cores burned inside galaxies. Those galaxies formed at the nodes of the cosmic web. The cosmic web is a structure of dark matter. Whatever dark matter is, whatever particle, whatever field, whatever form of matter we have not yet identified, it is not incidental to your existence. It is the precondition for it. Without dark matter, the early universe would not have structured itself quickly enough to form galaxies before cosmic expansion diluted everything into permanent uniformity. Without dark matter, halos providing the gravitational wells, gas would not have collapsed to form stars. Without stars, there would be no heavy elements.
Without heavy elements, there is no chemistry. Without chemistry, there is no biology. Without biology, there is no one asking what dark matter is. The invisible web is not background. It is the condition under which anything exists at all. The Millennium simulation has since been superseded by larger, more detailed simulations. Illustri, NG, EAGLA, Flamengo. Each incorporating ordinary matter physics, alongside dark matter, modeling star formation and supernova feedback and the influence of supermassive black holes on their host galaxies. Each successive simulation has matched the observed universe more precisely, and in every one of them, the foundation is the same. Dark matter flowing and clumping and webbing across cosmic scales, forming the structure that
once by observing it, counting galaxies, measuring redshifts, mapping the distribution of luminous matter across space, and once by simulating it, starting from known initial conditions and letting dark matter physics play out over cosmic time. The two maps agree. This agreement is one of the most powerful confirmations in science that our understanding of the universe at large scales is fundamentally correct. And yet the component that makes both maps work, the component whose gravitational influence anchors the whole structure, remains unnamed. We know its mass. We know its distribution. We know its behavior at every scale from dwarf galaxies to superclusters. We can simulate it. We can match it to observation across the entire observable universe.
We do not know what it is made of, not even in principle. Not even in the rough sense of knowing whether it is a single particle species or many, whether it formed early or late, whether it has any interactions beyond gravity, or whether gravity is its only contact with the world we inhabit, whether it is a relic of processes that happened in the first fraction of a second of the universe's existence, or whether it is something stranger still, something whose origin we have not yet imagined. We have mapped the skeleton of the universe. We have weighed it. We have watched it shape everything we can see and everything we are.
We have watched it pass through itself in a catastrophic 4 billion light-year collision, without flinching, without decelerating, without leaving any record of the encounter. We have built detectors of extraordinary sensitivity and listened for decades in carefully maintained underground silence. And yet, after 50 years of hunting, we still do not know what it is.
After 50 years of searching, some scientists began to ask a question that felt almost forbidden. What if the problem is not the universe? What if the problem is us? In 1983, an Israeli physicist named Mordechai Milgram proposed something that his colleagues found deeply uncomfortable. He was not suggesting a new particle. He was not proposing a new kind of field. He was suggesting that our most fundamental law of motion, Newton's second law, the bedrock of classical mechanics, might be wrong. Not wrong in the way that relativity corrected Newton at extreme speeds. Wrong in a different direction entirely. Wrong at very low accelerations. Milgram noticed something subtle in the rotation curve data.
The anomaly, the flat curves, the stars that refused to slow down, only appeared when stars were moving with accelerations below a certain threshold. Below approximately 1.2 times 10 to the negative 10 meters per second squared, a number so small it is almost meaningless to say aloud, an acceleration so gentle that it would take a human being more than a year and a half to reach walking speed. Below this threshold, Milgram argued, gravity behaves differently, not weaker, not stronger in the usual sense, but modified, following a different mathematical relationship between force and acceleration. He called his framework
modified Newtonian dynamics. Mond, the physics community, was not kind to this idea.
The theories that touch Newton's laws feel like attacks on the foundations of everything we know. Milgrom was treated the way Zwicky had been treated 50 years earlier, when he suggested there was missing mass in the coma cluster. He was noted. He was filed away. He was largely ignored. But the mathematics refused to go away. Mond made predictions. Specific, testable predictions about how galaxies should behave based solely on their visible mass. Not their assumed dark matter. Not their total inferred mass. Just what you could see. And in 2016, an astronomer named Stacy McGaugh published what became known as the radial acceleration relation. He studied 153 galaxies of every conceivable type. Spirals, ellipticals, dwarfs, giants. He measured their observed accelerations at every point.
And he measured the acceleration you would predict from their visible matter alone. The two quantities lined up, tightly, precisely. Across 153 galaxies, spanning a factor of 10,000 in mass, a single mathematical relationship connected what you see to what you measure. The relationship that Mond had predicted decades before the data existed to test it. This is not something that should happen by coincidence. If dark matter were a collection of particles distributed randomly in halos around each galaxy, there is no reason why the visible matter and the total gravitational behavior should follow such a clean, universal relationship. The visible matter does not know about the dark matter halo, and yet, somehow, they are perfectly correlated. Mond does not have this problem. In Mond, there is no dark matter. There is only the visible matter and a modified law of gravity. The correlation is automatic, but the correlation itself demands an explanation even within the dark matter framework. If dark matter exists, if galaxies are embedded in invisible halos whose distribution was set by the initial conditions of the early universe, why should the visible matter know about the dark matter halo so precisely? Why should the amount of luminous matter in a galaxy predict, with such clean regularity, the total gravitational behavior of the system? The two components, the visible disk and the invisible halo, formed through different physical processes at different times from different initial conditions. They should not be so tightly correlated.
And yet they are. Some dark matter theorists have proposed that the correlation is a consequence of galaxy formation physics. When a galaxy forms, the processes that regulate star formation, supernova explosions, radiation pressure from young stars, the accretion of gas, set an equilibrium between the visible and invisible components. The same processes that determine how many stars form may also determine how the dark matter halo responds. In this picture, the tight correlation is not fundamental. It is a statistical regularity that emerges from the physics of how galaxies are built. Others are less satisfied with this. The correlation spans too many orders of magnitude. It holds for galaxies that are tiny, isolated dwarf spheroidals containing only a few thousand stars.
It holds for the most massive elliptical galaxies in the centers of rich clusters. It holds for galaxies that formed billions of years ago and galaxies that are still forming today. A correlation that clean across that range looks less like a statistical accident of galaxy formation and more like a deep truth about the relationship between matter and gravity. Think about what that means for a moment. For 30 years,
Milgram's idea sat in the margins of physics, too radical to be accepted, too accurate to be dismissed. A formula written in the early 1980s by a man working largely alone that predicted the rotational behavior of 153 galaxies with a precision that the dominant theory of dark matter could not easily match.
The history of science is full of ideas that were correct before anyone was willing to believe them. And yet, science requires honesty, and the honest picture of Mond is not entirely clean. The bullet cluster does not care about Mond's success with rotation curves. In that collision of two galaxy clusters, moving at 3,000 kilometers per second, the hot gas was slowed by electromagnetic interactions. But the gravitational center of mass kept moving forward, untouched, passing through each other like ghosts through walls. In Mond, gravity follows the matter. There is no separate dark matter component to drift freely through a collision. But the bullet cluster shows exactly that drift.
A mass distribution that is clearly separated from the visible baryonic matter, following its own trajectory, as if it were made of something that does not interact with gas. Picture two enormous river systems colliding. The water, the gas, the plasma, is slowed and pooled and heated by the collision. But the river banks themselves, the gravitational channels that shape the flow, keep moving as if nothing happened. Something is providing that gravity, something that is not the water, something that passed through the collision untouched. Mond struggles with this. Its proponents have proposed extensions, workarounds, relativistic variants with names like Tevis and Aqual. None of them resolve the bullet cluster cleanly without reintroducing something that begins to look very much like dark matter under a different name.
And then there is the early universe, the cosmic microwave background, the faint thermal glow left over from 380,000 years after the Big Bang, encodes within its temperature fluctuations the entire acoustic history of the primordial plasma. The exact positions and heights of the peaks in that spectrum depend on the ratio of baryonic matter to dark matter in the early universe. Of 380,000 years.
They are like two maps of the same territory that overlap in some regions and contradict each other in others. The uncomfortable possibility, the one that serious physicists whisper about but rarely publish, is that neither framework is fully correct, that we are using incomplete tools to study an incomplete picture, that our understanding of gravity itself, even after 3 centuries of refinement, may be missing something fundamental. Newton looked at a falling apple and discovered a law that governed the motion of planets. Einstein looked at that same law and found that it was an approximation, correct in most situations, inadequate in others. Perhaps someone, somewhere, is working on the next correction.
Perhaps the correction will be one that explains both why Mond works for galaxies and why cold dark matter works for the early universe. Because they are both shadows of some deeper truth that we do not yet have the mathematics to write. Milgrom was not wrong to ask the question,
He was right to ask it, and the fact that we still cannot fully answer it, that is not a failure of science. That is science doing exactly what it is supposed to do, remaining honest about what it does not know.
When the leading candidate fails to appear, science does not stop. It branches. The history of dark matter research since the 1990s is a history of branching. Each null result at each detector opened a new corridor of possibility. Each empty signal widened the space of what the answer could be. And physicists, being physicists, followed every corridor. There are, at this moment, more serious hypotheses for what dark matter might be than most people realize. Not fringe ideas, not the proposals of amateurs in online forums. Peer-reviewed, mathematically consistent frameworks, published in the most rigorous journals in physics, each supported by at least some observational motivation. None of them confirmed. One of the oldest
Ordinary neutrinos, the ghostly, nearly massless particles produced in nuclear reactions, streaming through you in their trillions every second, are extraordinarily difficult to detect. But they do, occasionally, interact with matter through the weak nuclear force. They are at least somewhat social. Sterile neutrinos would be different. They would interact with nothing except gravity. No weak force, no electromagnetic force, no strong nuclear force. Gravity alone. They would pass through planets, through stars, through the entire observable universe without leaving a mark. They would be, in the purest sense of the word, invisible. The appeal is obvious. A particle that only feels gravity would cluster gravitationally, forming the halos and filaments we observe without ever triggering a detector.
It would explain why decades of WIMP searches have come up empty. WIMPs interact weakly. Sterile neutrinos would not interact at all. Searches for sterile neutrino signatures in X-ray observations of galaxy clusters have yielded hints. An unexplained spectral line at 3.5 kiloelectron volts, detected by multiple independent observations and stubbornly resistant to conventional explanation. Some physicists believe this line could be the decay signature of sterile neutrinos. Others believe it is instrumental artifact or astrophysical emission from known sources. The argument continues. This is what the frontier of physics looks like. Not dramatic announcements, not clean discoveries. A spectral line that might be something and might be nothing. Years of analysis, papers written and challenged and revised.
The signal neither confirmed nor refuted, simply sitting in the data, unresolved. Then there are primordial black holes. Stephen Hawking proposed in 1971 that in the extreme density of the early universe, random quantum fluctuations could have seeded regions dense enough to collapse directly into black holes. Before any star had ever formed, before any galaxy had assembled itself from dust and gas. These would be black holes born in the first fractions of a second after the Big Bang. They would have no light, no radiation beyond the quantum trickle Hawking himself predicted. And for black holes of significant mass, that trickle would be so faint as to be undetectable for the current age of the universe.
They would move through space without interacting with electromagnetism in any meaningful way. They would look to any instrument we currently possess
exactly like dark matter. Gravitational microlensing surveys, watching millions of stars for the brief brightening that occurs when a compact object passes in front of them, have constrained the mass range in which primordial black holes can make up all of dark matter. Large primordial black holes, in the range of tens of solar masses, are disfavored by the data from LIGO gravitational wave observations and microlensing surveys. But a window remains open in the subsolar mass range.
Small primordial black holes, perhaps the mass of an asteroid, perhaps the mass of a mountain, could still exist in sufficient numbers to account for the missing mass of the universe. There is a version of the universe in which dark matter is not a particle at all, in which it is, instead, an uncountable multitude of ancient black holes, scattered through every galaxy, orbiting at the outskirts of every star cluster, drifting silently through intergalactic space, the fossilized remnants of the universe's violent first moments. Black holes that existed before the first star, before the first atom had fully settled into the structures we now call chemistry.
Older than light, in the sense that the universe had not yet become transparent enough for light to travel freely when these objects were already present. Ancient in a way that no living thing can comprehend. And they might be everywhere, moving through the spaces between stars in numbers so vast they constitute the majority of the universe's mass. Beyond these, the theoretical zoo continues. Self-interacting dark matter, in which dark matter particles collide and scatter among themselves, creating cores in dwarf galaxies rather than the dense central spikes that ordinary cold dark matter predicts. Dark photons, hypothetical particles that mediate a mirror electromagnetic force among dark matter particles, creating a shadow physics sector that roughly parallels our own.
Fuzzy dark matter, made of particles so extraordinarily light that their quantum wave functions extend across entire galaxies, smoothing out small-scale structure through quantum pressure rather than thermal motion. That last possibility, fuzzy dark matter, deserves a moment of attention because the image it offers is genuinely strange. A particle with a mass around 10 to the minus 22 electron volts, so light that no analogy in ordinary particle physics applies, would have a de Broglie wavelength comparable to the size of a galaxy's core. Its quantum nature would not be hidden inside atomic nuclei, expressed only in the exotic conditions of particle accelerators. Its quantum nature would be expressed at the scale of entire galaxies.
A dwarf galaxy filled with fuzzy dark matter would behave not like a cloud of discrete particles, but like a quantum fluid, with interference patterns and standing waves governing its internal structure. The center of such a galaxy would not collapse to a dense spike the way cold dark matter predicts. It would instead form a smooth wave-like core, a soliton, whose size is set by quantum uncertainty rather than classical gravity. And the predictions of this model differ from cold dark matter in ways that current and near-future telescopes are beginning to have the resolution to test. Each of these frameworks makes different predictions. Each one modifies the universe's structure in subtly different ways.
Each one leaves different fingerprints in the distribution of galaxies, in the density profiles of halos, in the statistics of small, dark satellites orbiting large galaxies. What unites all of them is what they share with the original dark matter hypothesis. They are all attempts to name something that has not yet allowed itself to be known. They are all descriptions written from the outside,
inferred from the shape of absence. The gravitational shadows cast by something that produces no light, no detectable radiation, no signal of any kind that our instruments have yet been able to capture. We are building ever more precise instruments to look for those fingerprints. And as of today, none of them have been found with enough clarity to eliminate the alternatives.
Every failed hypothesis is a message from the universe. It is the universe telling us, not this one, not this shape, not this mass, not this interaction. Every narrowing of the possible is a kind of knowledge, even when it feels like silence. The universe is patient. It has been holding this secret for 13.8 billion years. It is in no hurry to share it with us.
So now we know what the candidates are. WIMPs, actions, sterile neutrinos, primordial black holes, fuzzy dark matter with quantum wavelengths the size of a galaxy's core. A whole garden of hypotheses, each with its own mathematics, each with its own silence, where a signal should have appeared. And yet, none of them have answered the question the web itself is asking. Not what dark matter is, but what it means that we are inside it. The web was already established, in Chapter 8, as real. The simulations matched the observations. The filaments were confirmed.
What we have not yet sat with, what the particle catalog does not address, is what it means to be a thinking creature inside a structure that was built entirely without you in mind. In the last few years, instruments have begun to image the cosmic filaments directly for the first time. Not through inference, not through simulation. Directly. LOFAR, the low-frequency array, a network of radio antennae distributed across Europe, has detected the faint radio emission from bridges of magnetized plasma threading between galaxy clusters. These bridges trace the dark matter filaments beneath them. They are real. They have been imaged. They are exactly where the models predicted them to be.
Square kilometer array, currently under construction across South Africa and Australia, will extend this reach dramatically. Its sensitivity will allow astronomers to trace filaments not just between massive clusters, but between smaller groups, down to the scales where individual galaxies are just beginning to be threaded onto the web. The skeleton will become visible in detail it has never been visible before. And when they image it, when the full filamentary structure is rendered in radio light, what they will be showing us is not the dark matter itself. Dark matter emits nothing. What they will be showing us is the ordinary matter that the dark matter has corralled. The gas that was funneled along invisible channels by gravity.
The baryons that followed a path they did not choose, toward nodes they did not determine, to build galaxies whose existence was already implied by initial conditions set 13.8 billion years ago. Think about the timeline carefully. The dark matter web began to form within the first few 100 million years after the Big Bang, long before any star ignited, long before any hydrogen cloud had grown dense enough to collapse. The web was a structure of darkness organizing itself in the dark, in a universe that had not yet produced a single photon of starlight. Galaxies came much later, hundreds of millions of years later.
They formed because the web had already prepared a place for them, because dark matter halos had already deepened the gravitational wells into which gas could fall. Stars came after galaxies. Planets came after stars. Life came after planets, after billions of years of chemistry. Creatures capable of looking outward came after life, after further billions of years. And us, this particular arrangement of atoms doing the looking, we arrived so recently that on a timeline from the Big Bang to today, the entire history of our species does not register as a mark. The web is old in a way that the word old cannot contain. It was shaping the universe for more than 9 billion years before the Earth existed.
It was already ancient when the first single-celled organisms appeared in Earth's oceans. Whatever it is, particle, field, relic of the universe's first moments, it has been doing its work in silence, without interruption, without any knowledge that anything would ever develop the capacity to notice it. This is the part that the particle candidates do not capture. Whether dark matter is a WIMP, or an axion, or a sterile neutrino, changes what we write in our equations. It does not change this. The web was here first. The web did not form in order to produce observers. It formed because of gravity, and initial conditions, and time. And we are here, inside it, because that process happened to produce the conditions in which we could exist.
You are not on the web the way an architect is in a building they designed. You are on the web the way a water droplet is on a spider's web, placed there by forces that preceded you entirely, held there by a tension you did not create, at a node you did not choose. The dark matter that shaped the filament you sit on does not know you are there. This is not a metaphor for indifference in the human sense. It is something more fundamental. Dark matter has no mechanism for knowing anything. It has no internal states. It responds to gravity and nothing else. It cannot be aware of what it has produced, any more than a river can be aware of the valley it carved.
The cosmic web is a structure of pure consequence. No intent, no design, no observation of itself. It simply is, has simply been, and within it accidentally arose the only kind of matter in the observable universe that has ever looked up. We mapped the web from the inside. We built simulations of a structure we cannot directly see. We sent radio telescopes across a continent to image filaments made of gas draped over an invisible skeleton. We did all of this while being, ourselves, a microscopic feature on one thread of the thing we were trying to map. There is something quietly vertiginous about that. Not terrifying. Not comforting. Something quieter than either. The web does not become more aware of us because we have mapped it.
The filaments do not shift when we image them. The dark matter that holds the structure together continues to do what it has always done, hold the shape of things, without any record of the fact that something within the structure briefly turned its attention toward the structure itself. We are the universe's only known attempt to understand itself from the inside. And what we find, when we look carefully enough at the largest scales, is that most of what we are looking at will never look back. Not because it is hidden, not because it is hostile, because it is the kind of thing that has no inside to look from.
Consider the numbers one more time. 4.9%. That is the fraction of the universe made of ordinary matter. Atoms, protons, neutrons, electrons. Everything that has ever been discovered, built, named, loved, or destroyed. Every star, every ocean, every book ever written, every person who has ever lived, every civilization that has ever risen or collapsed, the entire history of biology on this planet,
everything that science has studied for the entirety of human history. 4.9%. Dark matter is 26.8%. 6 times more than everything we have ever known. And yet, after a century of observation and 50 years of direct searching, we cannot tell you what it is. We cannot hold it. We cannot create it. We cannot destroy it.
We can only infer its presence from the shape it gives to things we can see. But the largest portion of the universe is not dark matter. 68.3% of the universe is dark energy, a term that covers our complete ignorance of why the expansion of the universe is accelerating, not slowing, as gravity would suggest. Accelerating as if space itself is being pushed apart by something with negative pressure. Something that fills the vacuum at a density that should, by the mathematics of quantum field theory, be either vastly larger or precisely zero, but is instead a small non-zero number that defies every attempt at theoretical explanation. We have no idea what it is, so the final accounting looks like this.
We understand 4.9% of the universe well enough to write equations for it. The remaining 95.1% is divided between 2 categories of ignorance that we have given names: dark matter and dark energy. Precisely because naming things is what we do when we cannot understand them. This is not a temporary situation waiting for the next experiment to resolve it. This is the condition of human knowledge as it stands today. After all the centuries of physics, after Newton and Einstein and Planck and Feynman, after the Large Hadron Collider and the Hubble Space Telescope and the Planck satellite and the LIGO detector, we remain quantifiably ignorant of 95% of what exists. Notice that the number has not improved.
In the decades since the Planck mission confirmed those figures, we have not moved the needle. We have confirmed the measurement with greater precision. We have mapped the cosmic microwave background with finer resolution. We have probed the large-scale structure of the universe with more galaxies across more of its history. We have built more sensitive detectors and listened longer in deeper silence. And the number remains. We have 4.9%. The projection of the universe we understand has not grown. What has grown is the precision with which we know how little we understand. There is a particular kind of silence that lives inside that number. Not the silence of a room at night, not the silence of standing in a library where 95 of every 100 books are written in a language you cannot read, and the books themselves are shelved in a wing you cannot enter, and the library extends beyond the horizon in every direction, and you were born in a small reading room near the entrance and you have never left it. The dark matter does not know that you are trying to find it. The experiments running right now, in mines deep beneath the ground, in detectors surrounded by tons of shielding to filter out every known particle. These experiments are invisible to what they seek. The dark matter passes through them as it passes through everything. The xenon atoms sit waiting in their tanks.
The dark matter moves through undisturbed. This is not an adversarial relationship. The dark matter is not hiding. It is simply indifferent in a way that has no human equivalent. It does not know what hiding means. It does not know what we mean. It does not know anything because it is not the kind of thing that knows. It was here before the first star ignited. It will be here after the last star goes cold, after the last black hole evaporates through Hawking radiation over timescales that make the current age of the universe look like a single breath. It does not participate in the drama of matter and energy that we call physics. It simply provides the gravity. It simply holds the shape of things.
And in all of this, in the 390 years since Galileo first turned a telescope toward the sky, in the 90 years since Zwicky first suspected that something was missing in the Coma cluster, in the 50 years since Vera Rubin sat up through cold desert nights, measuring the rotation of Andromeda, the dark matter has not changed at all in response to our looking. It does not adjust when we build better detectors. It does not retreat when we narrow the mass range in which it could be hiding.
It does not care that we have begun to understand the shape it gives to galaxies, or that we have simulated its behavior across the lifetime of the universe, or that we have written thousands of papers about its nature and found nothing conclusive in any of them. The universe was not designed around our ability to comprehend it. The laws of physics were not written to be legible to creatures who evolved on a small rocky planet to find food and avoid predators.
The fact that we can understand as much as we do, that the same mathematics that describes a falling apple also describes the orbit of a neutron star, that the same quantum equations that explain chemistry also explain the early universe. This is an extraordinary accident, and we should not mistake it for a promise that the full picture will eventually become clear to us. Perhaps it will. Perhaps some future generation will find the dark matter particle in a detector, will measure its mass and spin and coupling constants, will slot it neatly into an extended standard model and feel the satisfaction of completion. Perhaps the story ends with understanding. Or perhaps the dark matter is something stranger than any particle.
Something that does not fit into the categories we have built. Something that will require a restructuring of physics as fundamental as the one Einstein performed when he showed that space and time were not fixed and separate, but flexible and joined. Perhaps understanding it will require a new framework that will make our current theories look as approximate and incomplete as Newtonian mechanics looks to us now. Or perhaps the answer will never come. Perhaps the universe will always hold this particular darkness beyond our reach, not because the question is unanswerable in principle, but because the answer requires tools and timescales.
The dark matter was there when our galaxy assembled itself. It was there when the first hydrogen clouds collapsed into the first stars. It was there when the solar system condensed from a disk of dust and gas 4.5 billion years ago. It was there when the first living cell divided in the ancient ocean. It was there when the first creature looked up at the night sky and felt something it did not have words for. It is here now, streaming through you at this moment, not noticing you, not aware of you in any sense that the word awareness can hold.
Passing through the atoms of your body with the same complete indifference with which it passes through the rock beneath your feet and the void between galaxies. You are made of the 4.9%. You are a brief arrangement of ordinary matter in a universe that is overwhelmingly not ordinary matter. You will persist for a moment, cosmically speaking, and then the atoms that make you will disperse and become part of something else, and eventually even that something else will be gone, and the dark matter will still be here,
holding the shape of whatever comes after, just as it held the shape of everything that came before. The universe does not require our understanding to continue. It does not require our presence.
It has been running this dark architecture for billions of years before life arrived on this planet, and it will run it for billions of years after life has gone. We are the universe's way of looking at itself, for a moment, from the inside. And what we see, when we look carefully enough, is that most of what we are looking at will never look back. The dark matter surrounds every galaxy. It threads through every filament. It holds the web together across distances that have no human scale. It has been present for every event in the history of the cosmos, and it has never noticed that we were here.